Hello, my name is Angel Sunia. I used to work on DDC systems for processes in buildings. I want to share some basic knowledge with you in the following videos. The first one refers to heat exchangers. We will look at their static characteristic used in block diagrams for control systems. The next one presents a selection of well characteristics in applications with heat exchangers. The third one, we will walk through the control algorithm P, PI, PID and their use in processes. In the fourth one, we will look at the dynamic properties of HVAC processes and their degree of difficulty. In this video, we will see the following. Where are heat exchangers used? Dimensioning, static characteristic, and source of nonlinearity and linearization. So we are interested in the following processes: air conditioning, heating, and preparation of domestic hot water. Well, heat exchangers are usually dimensioned by the software provided by manufacturers. And we insert the nominal power and temperature into the software. Therefore, exchangers are designed for nominal power, but most of the time we know very well the system is only partially loaded. So therefore, we need to ensure that the power is adapted to current need, to current heat losses, or to current consumption of domestic hot water. So how to adapt power to current needs? Power is not controlled directly, but indirectly through temperature control. For this purpose, we use a closed-loop temperature control system. In the shown example, domestic hot water preparation process, the current heat demand is determined by the flow of the flow on secondary side, which changes and affects on temperature and therefore acts as a disturbance. So control process goes in that way. Controller measures the temperature and compares it with the reference value. Error controls the valve and this also the flow on primary side in the way to maintain the desired value on the secondary side. Well, this static characteristic is most often used in literature as evidence for nonlinearity of heat exchanger. Shows the relationship between power and flow on primary side for different value of temperature efficiency. For district heating applications, it means heating and domestic hot water preparation, theta is between 0.9 and 0.5. Characteristics are therefore almost linear. So this static characteristic would be useful if we had a system where the controlled variable is power. In our case, is the temperature, so we cannot use it. So what we are looking for is the static characteristic that will give us a relationship between temperature and primary flow. So let us take and calculate heat exchanger with the following data. Put this data in the software, exact, and which give us a certain type of heat exchanger. But first of all, let us try with calculation. Try with calculation to find characteristic that we are looking for. For this purpose, let us make assumption that temperature on primary side, return temperature on primary side is constant, and therefore also delta T on primary side is constant. We know that this is not true, but it will make calculation much easier. So we write equation for which gives us a relationship between primary and secondary power, and we express temperature on secondary side, and we get this formula. And if we present this formula in graph, we can see that there is a group of lines whose slope decreases with increasing on secondary, increasing of the flow on secondary side. And if we make a simulation of disturbance and how the controller react on this disturbance, let us assume that we are in the point number 1, and where the secondary flow is 600 liter per hour and is changed to 8 liter per hour, and this causes the fall of temperature on secondary side for 10 degrees from 50 to 40 degrees, and the controller reacts in that way that increase the output voltage, increase the flow, and try to maintain the same temperature as it was before. So desired temperature 50 degrees. And we see that for this change we need about 178 liter per hour, which means it is 33%. So if we make this process of disturbance and reaction of controller all along the value of primary flow, or with other words, all along the power, then we can see that that we need always 33% change of primary flow to eliminate an error of 10 degrees. It is 33%, but in liter per hours it is of course quite another number. At the beginning there is 59 liter per hours, and we can see on the end there is 444 liters per hour, but always 32%. We see that percentage are the same, but we need more and more change of primary flow in order to eliminate an error of 10 degrees, which means that the gain of heat exchanger is decreasing. And if we have a look also on the static characteristic made by exact, we can see that the lines are not linear anymore because of delta T is changing through the process. And there is no rel of equal percentage, because we see that 37% at the beginning is needed to change, and on the end is 50% change of primary flow to eliminate an error of 10 degrees. If you make a direct comparison of two static characteristic, calculated one and exact one, we see that calculated one have linear curves because the delta T on primary side is constant. And comparing with the exact one, where the curves are not linear because the delta T on primary side is changing from 55 to 45 degree nominal value, and the slope is not depending only on the ratio between primary and secondary flow, but also on delta T on primary side. And also there are different needed change of primary flow for eliminating the error of 10 degrees. If you have a look on the characteristic of the gain of these two types of static characteristic, it means calculated one and exact one, we can see that those curves are almost the same. So we can accept this calculated version and therefore also principle of equal percentage. However, we see that the gain is falling very much with the increasing primary flow, which means that relations between temperature on secondary side and flow on primary side is nonlinear, and this is not acceptable from the point of control view. So the heat exchanger is as it is, and we cannot change anything regarding characteristic. And so that's why we need to count on other components in the system and try to find the characteristic that will help us to linearize the system. And what kind of characteristic should be? So if we follow the rule of equal percentage and we have seen, as we have seen before, then this characteristic should be equal percentage. Gain of such characteristic is also equal percentage, something like this. System gain. Well, system gain is a product of the gains of all components. And so we can linearize the system by introducing an equal percentage characteristic anywhere in the system. It can be a controller, actuator, or well. And this will make constant system gain, and the controller parameters, so proportional band and integration time selected according to the known optimization method, will be optimal in the whole range of primary flow, and therefore also through the whole range of power. Thank you for watching, and I'm looking forward to see you in the next video.